Welcome back to another episode of Chaos Theory. In today's episode, we are going to talk about the famous notion of butterfly effect. The butterfly effect is the idea that small things can have non-linear impacts on a complex system. The concept is imagined with a butterfly flapping its wings and causing a typhoon. Of course, a single act like this, butterfly flapping its wings, cannot cause a typhoon. Small events can, however, serve a catalyst that act on starting conditions. The concept referred to as the butterfly effect has been embraced by popular culture, but the term is often used to emphasize the outside significance of a minute occurrences, as in the 1990 movie Havana, in which Robert Redford, playing the role of Jack Wheel, a gambler with a knack for math, proclaims to his co-star Lena that a butterfly can flutter its wings over a flower in China and cause a hurricane in Caribbean. So, what we can't talk about what the butterfly effect is, but what the butterfly effect is not. In the pop culture, the term butterfly effect is almost always misused. It has become synonymous with the leverage, the idea of a small thing that has big impact with implications like that of a lever. It can be manipulated to the desired end. This misses the part where the Lorentz insight comes in. The reality is that a small thing in a complex system may have no effect or a massive one, and it is virtually impossible to know which will turn out to be the case. Although the concept of the butterfly effect has long been debated, the identification of it as a distinct effect is credited to Edward Lorentz. Lorentz was a meteorologist and a mathematician who successfully combined the two disciplines to create a chaos theory. During the 1950s, Lorentz searched for a means of predicting the weather as he found linear models to be ineffective. As we have known in the first episode, what and how does chaos theory work or predict things? In an experiment to model a weather prediction, he entered the initial conditions. The result was surprising. A somewhat different prediction. From this, he deduced that the weather must turn on a dime. A tiny change in initial condition had enormous long-term implications. By 1963, he had formulated his ideas enough to publish an award-winning paper entitled Deterministic Non-Periodic Flow. In simpler language, he theorized that weather prediction models are inaccurate because knowing the precise starting conditions is impossible, and a tiny change can throw off the results. To make the concept understandable to non-scientific audience, Lorentz began to use the butterfly analogy. In speeches and interviews, he explained that a butterfly has the potential to create tiny changes that, while not creating a typhoon, could alter its trajectory. A flapping wing represents the minuscule changes in atmospheric pressure, and these changes compound as a model progresses. Given that small, nearly imperceptible changes can have massive implications in complex systems, Lorentz concluded that attempts to predict the weather was impossible. Lorentz always stressed that there is no way of knowing what exactly tipped the system. The butterfly is symbolic representation of an unknowable quantity. Furthermore, he aimed to contest the use of predictive model that assumed the linear deterministic progression and ignored the potential for derailment. Even the smallest error in an initial setup renders the model useless, as inaccurate as possible over the compound over time. Exponential growth of errors is a predictive model is known as deterministic chaos. It occurs in most systems, regardless of their simplicity or complexity. The butterfly effect is somewhat humbling, a model that exposes the flaws in other models. It shows science to be less accurate than we assume, as we have no means of making accurate prediction due to the exponential growth of errors. Lorentz insight called into question laws introduced as early as 1687, by Sir Isaac Newton, suggesting that the nature is a probabilistic mechanical model, a clockwork universe. Similarly, Lorentz challenged Pierre-Simon Laplace, who argued that unpredictability has no place in the universe, asserting that if we knew all the physical laws of nature, then nothing would be certain and the future as the past would be present to our eyes. Lorentz discovered that his deterministic interpretation of the universe could not account for the imprecision in human measurement of physical phenomena. He observed that nature's independent cause and an effect relations are too complex to resolve. To approximate the most likely outcomes for such complex systems as weather patterns, he began using sets of slightly different starting conditions to conduct parallel meteorological simulations. This method is still used today to generate our daily weather forecasts. Unpredictability plays no role in the universe of Newton and Laplace. In a deterministic sequence, as Lorentz once wrote, only one thing can happen next. All future events are determined by initial conditions. Yet, Lorentz's own deterministic equation demonstrated how easily the dream of perfect knowledge was founded in reality. The tiny change in his simulation might add so much that it showed by extension that imprecision inherent in any human measurement could become magnified into wildly incorrect forecasts. Yet chaos is not randomness. One way that he demonstrated this was through the equations represented the motion of the gas. When he plotted the solution on a graph, the result, a pair of inked oval-like figures, vaguely resembled a butterfly, known as Lorentz attractors. The shape illustrated the point that almost all chaotic phenomena can vary within limits. So, this was a short episode detailing about what the butterfly effect is and its origins and the use of it in the pop culture. Hope you like it. Signing out.